Okay. Looks good. There. Good morning, everybody. Let's see what we got going on here in the chat, just so I can see. Hopefully there's a few people in here. Yeah, we got quite a few. So, welcome everybody to the last week of CS202. Reminder for all you guys that our final is coming up next week on May 12th. So let's just kind of start the class to talk about some things. If you've got some questions, please ask them so I can answer them. But yeah, we just need to go over some housekeeping things. The first thing I need to mention is last week I talked about getting that assignment out there sometime before today. I did not do that. I had looked at the assignment and I found that there's a few things in there, mainly the exception handling part, that we have not gone over. And truth is, it's, at least in my opinion, it's not too important, and you will not really use exception handling, at least in your future classes. So I'm trying to make some edits. So at the end of today, I will have a new assignment posted. And I will give you guys until the end of next week to finish it. So on Wednesday, I'll talk a little bit about that assignment and run it for you guys. I think it's a fun one, and you will know how to do everything on that assignment. So that's housekeeping thing number one. Number two is that this is the study week, right? And so today I'm going to go over stacks and queues, and I think we're only going to take this one day for that. And then on Wednesday, I need a favor. Well, please come to class on Wednesday. We, as a department, have to give out ABET tests to verify whether or not the students have learned some of the main things that they should have learned in this class. So we're going to be taking a CS202 ABET test on Wednesday. It's not for a grade. I will end class early so that you guys can log into Web Campus and take that exam. Once again, it's not for any points. It just shows the department how well I did as an instructor, and if I missed anything, and what needs to be reevaluated. So please come on Wednesday to do that. Another thing is you guys should have gotten teacher review emails, I think. I know I got mine and submitted them. So if you want to let me know how I did and what you think of me, please do so. I do look at those, and I try to be better every semester. So feel free to do that as well if you'd like. A few more things. Grading assignment 9. I'm a busy man, but I will get that done this week as soon as I can. So please keep an eye out for that. And reviews. I will be posting final exam review coming up here pretty soon. The only thing that will be on that test that's not on the other 2 tests you've taken is stacks and queues, and we're talking about that today. So please stay engaged. We're almost there towards the end of the semester, and thank you for letting me give out my little speech here at the beginning. Once again, if you've got any of those questions, please let me know. So the first thing we're going to do is just kind of open our notepad today, just to get the basic things down for stacks and queues, especially the stuff that will be on tests. So let me get my nice little header going here. And now I know you've heard of stacks before. Does anyone know what a different name for a queue might be? In England, they use the word queue instead of something else. Does anyone know what that word is I'm looking for? Stacks and queues. Yeah, there we go. Awful got it. It's a line. And when we say line, we mean like when you go to the In-N-Out burger to get your shake and fries or whatever, and you have to wait in line, right? If there's people in front of you, you have to wait in line. So queues are lines. That's what they are. Nice job, nice job. And so what are these? Well, stacks and queues are really nothing new. They are just arrays. They are arrays. I guess we say very important data structures. Because they are arrays, we can use a dynamic. Well, we can use just a contiguous array in memory, right? So we can use static or dynamic arrays, or we can use linked lists. Your favorite, I'm sure. Okay, so overall, it's just nothing new. But there's a few things about stacks and queues that we need to talk about, and it's just how they're worked with. Okay, they're actually very simple. They're exceptionally simple, and I know that you guys will appreciate how simple they are. So with a stack and a queue, the main thing is you cannot remove an element from anywhere in the middle of that list. Anywhere in the middle of that list, the elements will stay. So there's only 3 functions that work with stacks and queues. So let's talk about that. There's 2 main functions and a third one for fun. I call it one function for fun. So whenever you're talking to your computer scientist from 1966 or whatever, they're not going to know about this fun function. They might. But when it comes to things like Turing machines and stuff like that, you'll learn about that in Automata, which is CS456. They will not have this third function that I'm talking about. So the 2 main functions are, I guess we'll start with push. Now this one may also be called NQ in the stack. So let me do that. We can do NQ. Not for the stack, but for the queue. For this class, we're just going to use the term push. That's very common. And you'll notice that when we use vectors before, we use something called push, right? Push back. So push is function number 1. And what does that do? Well, that inserts an element to the list. Now the next one, you probably guessed it, called pop. It's just called pop. I guess in queues, it would be called DQ if you want to get fancy. So once again, for this class, we're just going to stick with our push and pop. And then the last thing I'm going to talk about here is this is the for fun function. This is the for fun function, which is helpful in our programs, and that is called peek. I forgot to add my definition here, so let's do that real quick. Pop, that removes one element from the list. It also returns that element. So in a way, this is like a void function. Push is insert, it's a void, and this is a whatever the element type is. Right, I already said that. So whatever type the element is. And then peek is pretty much it's pretty much pop, except it doesn't remove that function. So it just shows what the top element is. It does not remove it. So this is kind of nice because we can look at what's on the top of the stack or at the back of the queue, and we can say, hey, what is this thing, before we actually take it out of that data structure. So usually we'll have a peek, and that just helps us sometimes with our code. So that's really it. I'm going to make some whiteboards today, and I'm just going to finish up some notes here to make sure that we got everything. There's a few more things that I do want to talk about, I know that. So the first thing I need to go is here. Yeah. Let me see what this says. Yes. I forgot something very important. So first thing I'm going to do is put this parameter in here, meaning that it takes a parameter. But these peek and pops, they do not take any parameters. So now let's talk about the kind of test question. This is what someone will ask you all the time. And this is how we remember the difference between stacks and queues. FIFO and LIFO. So can anyone tell me what these stand for? I know that you probably know it. Or someone knows it. You can just give me one if you want. Yeah, there we go. So T. Peter and C-Bay got the FIFO part there, right? That's pretty easy. That means first in, first out. And so LIFO, you probably guessed it, is last in, first out. So we're just going to demonstrate this a little bit with some whiteboards. This is a pretty simple concept, I do understand. It looks like a lot of people left the stream because they know what these are already. And I'm spilling water everywhere. How embarrassing. But we'll just do some whiteboards. We'll put a little bit of code, and then we'll be good. And so, let's get out our paint. So we're just going to make a queue and a stack, just to kind of show you what they look like. And so kind of what we've got is maybe a line. I'm going to actually pull open an old image that I've had before, and I'm just going to kind of screenshot things over here to keep things simple. Let's see here. So the first thing that I'm going to do is I'm just going to put down here that this is a queue. We'll start with the queue. This is a line, and how does that work? That works, the queue is actually the LIFO structure, and the FIFO structure is the stack. So if we got to add that probably in our notes here, we're going to say that this is for the stack, And this one, well, no, I'm probably getting that mixed up. I think this one's the Q. Let me check my notes. This is kind of like with the insertion operator and the extraction operator. I'm always getting them mixed up. But yeah, that's correct. So then the LIFO is the stack. So the first one who goes into the queue is going to be the first one that comes out of the queue. And then the last one that goes into the stack is the first one to come out of the stack. This one's kind of unfair, in my opinion. At least if you're thinking about it in terms of if you go to in and out. if they were doing a stack at in and out, you would think that's unfair because you would have been the first one there, but then you would just have to wait as people stacked on top of you to get their burgers, and then you would hope that eventually you would get to the counter. So with the queue, I imagine that we kind of do this thing here where we push some elements on. So the first thing that we'll do, let's pretend that we push these in. So let's pretend that we do 4 push statements here, where we push in, we're working with integers here. So let's push 3, 5, 2, and 20. So the first thing that's going to come on is this 3. That's kind of number 1. So this is going to be our stack, or queue. Let me kind of make a line here. So the way this one works, as always, is that the kind of goes in like this. You go in like this, and then they come out like this. So then if we're going to push a 5, a 2, and a 20, then you can imagine that they're all going to go in here like this. Let me do this instead. So they'll all kind of pile in behind here, this number 3, just like that, where the first one in here was the 3, and then the second one was the 5, the third one was the 2, and then the last one was 20. So then if we call peek, peek is like the pop in which we'll just look at an element. So in a queue, when we have the first one in, first one out, what is the first one that was in this queue? Well, it happens to be this 3 here, right? So peek will let us look at this element. If we called peek on this queue here, it would say that's a 3. And so the moment that we actually call pop, grab it here. Wow, let me do a few things. I'm all over the place. It's a little rough. So peek, that shows us 5. And then we'll finally call pop. Pop doesn't take any parameters at all. And so it happens that when we call pop, it's actually going to take that 3 out of the queue. Just when they say in and out, order, well, when you pay, then you go to the waiting area, right, for your food, and then you get out of that queue. So when we call pop, we're actually going to take this exact same thing here. And this guy is going to come out. Let's see. We got some knowledge here in the chat. Oh, that's interesting. I'll have to look at that. like that. Oh, I see. Oh, that's cool. Oh, and it saves it to, oh, that's cool. Thank you. So, this is pretty much it for this. So, let's pretend that we are now looking at this just so I can verify your understanding of what a queue is. The next time I call pop on this, what comes out of the queue? I'm asking you guys. I know it's easy. Just please tell me if you know or I need to spend more time. Thank you. Red Rose says we call pop. That 5 will come out of there, right? That 5 will come out. And then if we call pop again, the 2 will come out. And then we call pop again, the 20 will come out. As we push more things in, it will go in up here. And then when we call pop, they come out down here. That's it. That's how the queue works. So now a stack is the other way but backwards. And if this is the one, well, of queues and stacks, I'm guessing the stack is the one that you're probably most unfamiliar with. Not to say that you are unfamiliar with it, but I didn't know what a stack was really, at least the definition of one, before I took classes here. So all we'll do is delete some stuff. All right. So this is now our stack. Stacks are cool because they preserve the order of things. Queues also preserve the order of things in a different way. But in a sense, stacks are really nice because of recursion. So where we get stack overflows. And so the way that this one works is like this. This is the push. And this is the pop. So down here, or the queue, we have this arrow down here. But in fact, things will go in and come out. And a good way to think about this is if I want to get this 3 out, this 3 can't fit. Okay, so this, if you know, theoretically, I was like, I want to get that 3 out of there. The 3 can't just pummel through these other elements and come out the top. It is stuck down here. As if there's a bunch of pancakes on top of it. It can't come out until these other elements come out. And so when we call peak, it's pretty simple. It's going to show us 20. Because that's at the top of the stack. Let's see here. I see we got something going on there in the chat. Yeah, exactly. Yeah, come up with all the metaphors you want for this. Red Rose says it's like stuffing Pringles into a Pringle can and then taking them back out. You can try to get that Pringle out from the bottom of the can, but it will be very difficult unless you take out the other Pringles first. So pretend even like here, it's like a bucket almost, right? And they can't even come out this way. Boop. And so remember that this one is LIFO. The last one that was in is the first one to come out. So recall that we pushed, I'm just going to show you this. We pushed 3 in here, that's down here. Then we pushed 5, that's here. And then we pushed 2, that's here. And now I push 20, so 20 comes in, lands right here. And then when we call pop, it says the last one that was in here is now the first one that was out. So the last one that was in here was this 20. So we call pop, now this one comes out. And then the next time we call pop, 2 will come out. And then the next time we call pop, 5 will come out. So we call pop, the 2 comes out, so on and so forth. So I'll just show you that one. And then we can just kind of code these up real quick. There's not a whole lot of code associated with this. If anything, they're simpler than the other arrays that we've done before. Because the insert, you know, we're not inserting between any elements. Stuff like that. We might as well do it with a linked list since you'll have to do it in the assignment. but it'll be mostly not too bad. So just so you know, if I copy this and I call pop, guess I deleted it, huh? Okay, so I'm going to try this knowledge thing here. Wait, never mind. I don't need to. I will in the future. So now if I call pop here, it's not really going to fit. Of course, this 20 comes out. There it goes. So it's like the other way around. But that's it. And that's only the difference. And you will need stacks and queues for specific things. Specific algorithms that we talk about in computer science in the future. Like I said, Turing machines, you need stacks, like push down automata. But I won't scare you too much yet. Things like with scheduling as well, scheduling jobs. It all kind of is based around these things. And for the assignment, I'll tell you just a little bit about what you do. Like I said, it's really not finished yet, but I'll show you the little image I made. You're going to just kind of test the effectiveness of stacks and queues when they're used against each other with some evaluation metric. So I'm going to show you this little image that I made in Microsoft Paint. So the assignment that you're doing is based around, why are you doing that? There we go. It's based around 2 restaurants, okay? Now these restaurants are in the, I kind of moved myself, didn't I? These restaurants are like in the future. You know that movie WALL-E, where everyone's getting their nutrition from cups and stuff? So somewhere in the future, like, these people only care about getting their food fast, okay? They don't care about the quality of the food because the food is all the same. And so all they care about is getting their food fast. So in one of these, you're going to have a stack, and the other one you're going to have a queue. And so if a person gets their food fast, they'll give them 5 stars. If they have to wait a few seconds, it will be 4 stars. Wait a little bit more, 3, 2, 1. And if they wait too long, then they'll actually leave the line and give the restaurant a 0-star rating. And so you'll have 2 stores, and I've kind of coded out the timing stuff for you. But one of these is going to be a stack. Like I said, it'll be unfair. And so people will be stacking in front of these people. And we'll see which one gets the better rating. And it's kind of fun to think about because in a stack implementation of this, one person, I mean, let's pretend it's Future Burger here that is using the stack. Future Burger can guarantee that every time they serve somebody, they get a 5-star rating. And there's a chance that they might be able to get to this person and this person if someone doesn't come in the door, you know, to hop back on the stack. But they will also have quite a bit of people who leave the restaurant with giving 0-star ratings. And here, say at Pizza Shakes, they're doing the queue. They cannot guarantee that they'll get a 5-star rating on every serve. Because most likely, this person has been waiting in line for a while. And so it's kind of fun to think about, just to compare, you know, how a stack and a queue look, and see how they kind of have some, what's the word I'm looking for? Some usefulness in kind of different situations. So that's kind of what the assignment is. So all we're going to do is just kind of code up our stack and stuff. I want to make sure that I don't have anything pulled up here that you shouldn't see. So let me go black for a moment. Does anyone have any questions so far about what's going on with the stacks and the queues? I think it's pretty likely that people are understanding what's going on. I'm sure you've got some metaphors going already. And you know what I'm going to say is I'm going to do our example with some inheritance. I think that'll be fun. One before. So CBA asks, stacks are LIFO and the one before is FIFO. Yep. Let me just, I gotta close this first because I don't want you to see it. I don't want you to see it. Lessons, we'll go here. Yeah. Can I have this here, please? Nice. All right. All right, so I'll come back here. I'll come back into view. Here we are. And so CBA asked, let me just make sure I got it in the notes. So, yeah, here it is. So let me make sure that we're on the same page. Stacks are LIFO. Yeah, stacks are LIFO. And queues are FIFO. So, yeah, I'll be sure to upload these notes so you can remember. And I'm telling you now, this is definitely a test question. I'm going to say, what's the difference between a stack and a queue? And how are you going to explain it? Use these, you know. Or I might ask you, what does FIFO and LIFO stand for? So remember this. I'll also upload those little whiteboards. If you've got any more questions, please let me know. So right now, I'm going to kind of pull this over here so that we are using up most of the screen, at least the part of the screen that you can see. All right. And over here, I'm going to create our stack and queue.cpp. So let me get my favorite stuff in here. Stream. Using namespace std. And to keep life easy, we're going to do a linked list today, okay? We're not going to do a template. We're just going to do a linked list. So I'm going to get a struct node going here. And it can be a doubly linked list. Let me make this bigger. And let me pull this out of the way. So if we're not going to do a template, let's just kind of make our example like we did on the whiteboards. Keep things nice and exciting, obviously. Working with integers here. In your assignment, you'll be working with a customer class. So we'll have our data, and then of course we'll have our node previous and our node next. Should work like this. Okay. Will you turn green, please? Thank you very much. So let's do a class. I'm going to do some inheritance. That's what I said. Just to show you that they're so simple that we can kind of do this. So what I'm going to do is I'm going to call it a kind of like stack queue or something. I want to call it a line, but that's what we did in the assignment. So I'll call it a stack queue. We'll call it a line. That's fine. I'll put in a comment here, not to be confused with queue. Okay, this is the base class. It will either be a stack or a queue. Okay. So when you think about a line, I just want you to think about that silly image I showed you, where these are both kind of lines, right? People are waiting in line, except one of them is a stack and one of them is a queue. And so in our, I'm going to do protected, since we're going to do some inheritance here today, and I'm going to do public. And in fact, most of our stuff can be handled here inside the inside of this class, though I am going to make it abstract. So the first thing that we're going to need is probably a node head, right? This is going to be the top of the stack or queue. Now, usually, stacks and queues will start empty almost always. Okay, I mean, we can implement a constructor to like create one if we want, probably like a copy constructor. So maybe we'll do that. But other than that, we really don't need anything other than the copy constructor and the default constructor. So let's go ahead and keep it int size, just because I always like to do that. And let's make our constructor. So let's say we've got a line here. And we're just going to initialize these guys as we always do in the default to be null pointer and the size to be 0. There we go. And so then I said we want to do kind of these copy. We want to do the rule of 3, right? So let's do that. Let's get our destructor going. And let's kind of just do a traversal while loop as we always do. Traversal is equal to the head. And we'll say while the head does not equal null pointer. We're going to delete the head node. And we'll say that the head node is equal to head next. Now this will kind of help you in your assignment just because I have coded it up already and I have tested it. So if you're going to be doing something that's deleting something from the queue or stack, this is the destructor, so it really doesn't matter, but it's always good to check for this. So I'm just kind of giving you this code here. It's kind of good to check for this in DLL. I did this wrong, folks. I really did this wrong. I really did this wrong. I think we'll do this. My bad, folks. Getting ahead of myself here. So we'll say that the traversal is equal to the head node. I don't know why I need to do this. I've done this a million times before. All right, there we go, right? Save the node. And then we'll move next, and then we'll delete it. And what I want to say is if the head previous does not equal that null pointer, then let's go ahead and let's just set it to null, okay? Like I said, this is the destructor, so it really doesn't matter. But this is always good to kind of check for, just in general, right? Because it's a DLL, right? This is a doubly linked list. So we do have to keep in mind what these previous nodes are equal to. And so if we're going to be deleting whatever the head was, then we want to make sure that whatever is the next node is not looking back at that old memory, right? That's kind of a dangling pointer. So that should handle it. If any of you see anything wrong with that, let me know. I mean, we'll find out. And then if we're going to do a copy constructor, let's do a few things. I'm actually going to take this out. Let's make a clear list. Just put it there. How's that? And then in the destructor, we'll just call that clear list. So this will be our default constructor here. This will be our clear list used in the destructor and assignment operator. Then we've got our destructor here, which we'll call clear list. This is all stuff we've seen before. I'm sure you guys are nice and bored out of your minds. Though it's always good to go over things again, and that's how we learn. So now we'll do our copy constructor, just because that one's easy. But it's only easy if you got your assignment operator right. Okay? So if we're going to do a line, we're going to need a const line ampersand, and then you could say the copy here. And all we have to do is say this dereferenced is equal to the copy, right? Now we'll do our assignment overload. What is this one? This will be void operator equals, right? And in here, we're going to take this const line copy. You might want to name this right-hand side. And so the first thing that we should do is call clear list, right? And it will handle this in case the list is already empty. Make sure that we do this real quick to make sure that we don't have any issues here. This is where I got screwed up last time. I don't know if you remember with the size and stuff. But if we're going to be calling this operator equals, if we need to initialize that head to null pointer so it knows that this check will be good to go, right? So it knows that it won't execute this at all. So we'll just call clear list, right? And then we'll say if, you know, the right-hand size equals to 0 or something like that, then we'll just return. Else, we can just kind of move on and copy that list. So let's do that. So we'll say that the head is equal to a new node. I like to prepare the heads previous to be equal to the head next, which will be equal to the null pointer. Just in case, right? As I've always said. And then we'll say that this head, its data, is equal to the data in the other list, right? That'll be the right-hand side dot head dot data. So now I'm going to use two traversal nodes since I don't have a bracket operator. We'll just quickly go through that. We've done this a million times before, maybe not this one specifically. So we're going to have the, I'm going to call it the this traverse is equal to this head, right? And I would also like the node, the right-hand side traverse is equal to the right-hand side head. And all we're going to say is while the right-hand side traverse next, not previous, next, does not equal null pointer, then we'll say that this traverse next is equal to a new node. And while we're in there, once we've done that, we've allocated from that next pointer, we can say that this traverse is equal to this traverse next, since we've just allocated it. And we can say that the right-hand side traverse is equal to the right-hand side traverse next, since we know that it's not null. So what did we do? We allocated and then move to next. And now once we're there, we can copy all of the data that we want. So the first thing that we'll do is we'll say that this traverse is going to be equal, the data at least, is going to be equal to the right-hand side traverse data. Man, linked lists are so much fun. Once we've copied the data, let's make sure that we assign that previous node, right? So let's take that previous node and let's assign it to, oh boy, I kind of messed that up. Can't do that yet. Can't do that yet, folks. Sorry about that. See, I kind of ran into a little error there. So since I didn't move it, I just have to throw in these nexts everywhere. And I know it looks disgusting, but you will have to do this on your assignment, okay? So I'm kind of giving you some ideas here on what that looks like. So what's the previous equal to? Well, that's equal to this traverse, right? So we'll copy the data, assign that previous node. let's also make sure that we get the null pointer going just in case this ends. And then we're ready to move to the next. So that should do it. I'm just going to take one breather here. I know that was a lot to just check my code with my eyeballs. So we clear that list. We know that's probably good. We'll check to see if the size is 0, and if it is, let's get out of here. Else, we know that there's at least a head node. So we'll allocate our head node. Prepare, just in case, the right-hand side size is 1, and then copy the data. Now, since we're going to go through each list one by one, we need 2 traverse nodes for each list. Because we never want to lose that head, right? That head always has to be looking at the beginning. So we'll assign this traverse and the right-hand side traverse. And we'll say, hey, as long as the right-hand side traversal node next does not equal null pointer, then we know that there's a deep copy to be made. So we will allocate that deep copy there. So the first thing to do is allocate it. And then we'll assign the data in there. And then we will assign the previous of that new node to be looking at the right node. This is a DLL thing. And then we'll prepare the next node just in case it ends on this iteration. Finally, to make sure we don't have infinite while loop like I did last class, we will make sure to move both this node to the next one and this node, the right-hand side node, to the next one. Okay, so that should kind of wrap that up there. We also might want a size plus. Or we can just kind of do it this way. We can just say, hey, our size is equal to the right-hand side that size. Right? Okay. So now that we have the not so fun stuff out of the way, let's finally get into our actual queue and stack stuff. Because I handled my rule of 3. So now we have to do a push, a pop, and maybe a peek. Okay? Now, I'm going to ask you guys kind of a question here. Well, it is a question. But I do kind of want to maybe throw my other classes down here so you maybe have an idea. If I want my line class to be abstract, okay, so the queue and stack are both going to be inheriting from this line class. They're both going to be inheriting from this. Now, a queue and a stack will both be using a head and a size. A queue and a stack will both initialize their values to be this. A queue and the stack will also clear their list like this. They will also copy their list the same way. And they will all, yeah, I mean, I said that. They'll copy the list the same way. So now when it comes to doing these functions, a pop, a push, and a peek, do you guys have any guesses on which ones can be done in the line class, meaning that it will kind of be the same depending on how we implement it, and which one should be done in the other class? Meaning, which of these functions should be virtual? Let me ask this question. Let me put it here. I just kind of want you to think about it, because we do this in the assignment. And so here we'll have a queue stack, a queue, and we'll have a stack. We'll have a queue and a stack. So let's inherit class queue, which will be inheriting publicly from the line class. And we'll have a class stack, which also inherits from the line class. CBA says the pop should be virtual. I do. That is true. That is true. So actually we have a few options here, and we'll do CBase. Yeah, so T. Peter says the push as well. So let's talk a little bit about it. The peak I'm going to remove just for a little bit because it's going to get confusing. So, yeah, I just kind of want to, I want to see the best way to do this. So if we made pop virtual, then push would be the same for both of them. And so pop, if it were to be virtual, let's say in pop, the stack would remove the head element, right? The queue would return the element at the end of the list, okay? So that's correct. I like that. And then the push could be the same. I just kind of want to, yeah, that's okay. So if we made pop virtual, then push would be the same, as I said. And that just means we'll put in the new element to the head every single time. Every single time we'll just insert that new element to the head. So we'll do that one in today's class. I think the one in the assignment is done with the push, but maybe I'll leave it up to you guys. And so all we'll have to do is if the stack, then we'll just return that head element. And if it's in the queue, then we'll just go all the way to the end of the list and return that element. Now the push could be the same. I'll just put it here in the notes. If we made push virtual, then I'll just shorthand it, the stack and queue would insert elements differently. And that's because the pop would be the same. Meaning, if we were to do the push virtual, then in the stack, we would just push it right onto that head element. But if it were in the queue, we would go to the end of the list and insert it there. So if you're not confused yet, let's just do one of them. Okay, let's just do one, the one that CBase said, since that was the first answer in the chat. So what we'll do is pop is virtual. Pop will be the type of this list. The type of this list is an integer. Okay, it's an integer. So that means int pop equals 0, right? I need to make it virtual. And then the other one will be a void push int item. That one will not be virtual. So let's do it as the way that I had kind of explained. Very easy, right? All we're going to have to do is say, hey, node, new node is equal to new node. And then we'll kind of do our fun stuff, right? So just like always, we got to insert that data. And we got to say, hey, the new node next will be equal to the new node previous, which will be equal to null pointer. Okay. And then all we're going to do is this. We'll say that the new node next is equal to the head node. Head might be null pointer. And then we should check to see if the head was null pointer. So if head does not equal null pointer, then let's make sure that the head previous is looking at the new node. If head is null pointer, then you'll get a seg fault here, right? Well, if you didn't have this if statement, and you just said head previous equals new node, we would dereference a null pointer. So you have to check for that, and then once you do that, we can just say that the head is equal to the new node. That's it. It's all pretty sure. Maybe I'll do a size plus plus while we're in here as well. And let's just take a moment to look at this code, make sure I'm not too excited, and I hope that I won't get any errors doing this. I'm sure we will have one or two. So I do my allocation stuff here, right? Allocate that. Copy data. prepare. This is the prepare step. That's what I like to say. Prepare. And then we'll say, hey, let's do the next assignment. If head will be null pointer, then we're good. And if it's not, then we're still good. And then we'll check to see if that head was equal to null pointer. And if it's not, then we'll make sure that the previous node is good to go. And then we'll say, hey, the new head is now the new node. Now, if you want to avoid that alias, which is always good practice, right? We can avoid that alias. We're good to go. So that'll be our push. Okay, we'll just push it in the head. So now, this is the only thing that's virtual, right? Let's go handle it. So guess what? There it is. We'll fill it out in here, and we'll fill it out in here. And then we'll do our main implementation, and then we'll call it a day. So the stack one is actually the easiest. The stack one is the easiest in just the way that we're implementing it here. It's the easiest one, at least the way I think so. So all we have to do is say, well, I'm going to save the node. I'm going to delete node. That's what I always call it. It's equal to that head node, right? We're also going to want the return data is equal to whatever was in the head node. And then we'll just say head is equal to head next. And then we'll delete the delete node. Maybe we'll say size minus minus. And then we will return, whoa. There's a few things that we need to do. I'm getting ahead of myself. And then we'll return the return data. So let me ask you, I know that it's kind of hard to follow, but there's one thing I said I forgot here. What do you think that we might do? I kind of already did it up there in the clear list function. I also did it in the push function. Do you think there's anything here that I should do? You can say it shorthand, you know. What do you think? I'm going to kind of fill in my comments here while I'm waiting. Yeah, Red Rose nailed it. Nice job. Thank you. We're gonna want to edit a previous pointer node. We're gonna want to edit that to make sure that everything is good to go. Save the data. Move head to next. Deallocate the old node. Subtract size. And then we'll say, hey, if the head does not equal null pointer, let's say that the head previous is equal to null pointer. Right? Because now there's nothing behind it. We just deleted it. Here it is. We deleted it. That was the node that was behind the new head. So since we deleted it, the new head's previous doesn't need to look at anything. Handle DLL, prev pointer, and then we'll return the data. All right, so that's our stack pop. Pretty easy. We could also implement a peek. I'll be sure to do that. Now let's do this pop, okay? This one will be a little bit different, but mostly the same. The first thing I'm going to want to need is a traversal node, since we're going to go all the way to the end of the list, right? Let's refresh our memories here. This is Q in class. So if we're looking just at this thing here, notice that the head node would be pointing here, right? In the way we're implementing this, the head node would be pointing here. And so if I call pop, I'm going to want to go to this node, and then I want to go to this node, and then I want to go to this node. And then I want to return this thing. So that's kind of what we're going to have to implement here. As I'm thinking about it, I do want to do this first. if head equals null pointer, let's say that the stack is empty. Now, this is not good practice, really. You would rather check to see if the stack actually has stuff in it before you call it, but this is good to have. Just in case the stack is empty, then let's make sure we don't dereference it. Right here, we dereference it, we get a segfault. So I do want to do that in the queue as well, just in case that the queue happens to be empty. Else, then we'll do our node traversal, which is equal to the head node. And we'll say while traversal next does not equal null pointer. Then we'll just travel on down to the end of that list. So we'll travel down to the end, like I said. I kind of did it here in the screenshot, right? We're going to travel on down to 3, where its next is equal to null pointer. And so once we're there, we're going to want to kind of do this thing, this exact thing that we did here. I'm going to kind of copy it, and we'll kind of edit it as we go. So we probably don't need this, since we already have a traversal node. But we do want to save that data. Okay, so the return data is going to be equal to the data that's inside that node, right? So in this case, it'll save that 3, like my kindergarten squiggles here. We don't need to do this, because we're already at the end of the list. Then we're going to want to delete this node, but before we do that, I would like to do the previous... I'd like to do an update first. So let me move this stuff down here. So let me ask you guys, I'm going to have to do some previous update here. Does anyone have the idea of what that code might look like? Here, let me do this. I'll give you the first part of it. If the traversal previous does not equal null pointer, what should I put in here? And while we're doing that, I'll kind of I'll kind of refresh ourselves on what we did, because I know I went kind of fast. So if our queue is empty, else start at the head, go to the end, then we'll save our data. And now I want to do a previous pointer update here. And so recall this, if our queue only has one item in it, then its previous will be equal to null pointer. So this code won't execute. But if not, right, if not, then we'll be looking at this 5 here. This 5 needs to have an updated element. So I know it's not too often I ask you for code in the chat. So I'll just give you a few more seconds, and then I'll give it to you, and we'll move on. But once we do our previous pointer update, then let's delete that node. And then let's subtract our size, and then we'll just return the data. So this one gets a little convoluted, but all we'll do is say, hey, the traversal's previous next equals null pointer. That's the fun little one-liner I was looking for. I know that's kind of difficult. Right, so just from that end node, I'll go to the previous node, and then I'll look at the next node, which is the traversal node, right? But I'll just say, hey, forget about me. That's what's nice about the DLL. We can travel both ways. What did I do here? I traveled back, and then I traveled forward again, kind of. Okay. So do we have any questions about these? I mean, it's more linked list stuff. if we were doing dynamic memory allocation, instead, it might look a little simpler than this. But with linked lists, it's always good to kind of practice this stuff. So let's do a peek just for fun. It'll be a constant because it's not going to edit the thing at all. I'm going to check this exact same thing. In this case, I'll just say that the line is empty. That says stack is empty. This needs to say, one of them needs to say that the queue is empty. Else, well, I don't need an else here. We'll just return the head data. Right, this one's nice because we don't have to delete anything. Oh, wait. No, the peak is, no. The peak will be different for both of them. Maybe we'll hold off on it for now. Because for one of them, we'll need to travel all the way to the end. Let me do it this way at least. I'll save the peak, but I'll just put it in the stack. Put it down here in the stack, and then maybe we'll hold off on the Q one for a moment just to at least verify that we've got some working code. We'll just kind of test it in main. We'll do our same stuff that we were doing before. So I'm going to declare a stack, and a Q. These are going to be pointers, because guess what? We're doing virtual functions. Isn't that fun? New stack. And this is going to be equal to new Q. And you'll notice that I messed up here. These need to be lines, since we're doing virtual functions, right? We don't have to, actually. I'm thinking about it. It really doesn't matter, actually. We'll do it this way, though. We'll do it this way. Okay. So let's just look back at the whiteboard that we did. We'll start with the stack. So the first thing that we did was we pushed on a bunch of elements. So first we pushed on a 3. And then we pushed on a 5, a 2, and a 20. And so then if we call peak, which we can, why not? Since we did it for the stack. We didn't do it for the cube, but we did it for the stack. If we call peak, no, I can't do the peak. Not unless I do it this way. Now, here's a good question, though. Well, I'm not going to spend too much time on it. This was a question on your test, if you remember. The peak needs to be overridden, or what's the term? Yeah, override. The function needs to be overridden in the Q class too. Otherwise, Q will be abstract. So I am going to do this. And for now, we're just going to return 0. If I get the time to implement it, I will. Just so Q's not abstract. So let's just peek at the top to make sure that it's right. And then all we'll do is see out the stack pop a few times. And maybe somewhere in here, I'll call stack push on a new element so we can see that it works. 999. So what should we see? Well, if we're going to peek at the top of the stack, it will be the last one that was in, right? The stack is the LIFO, right? So yeah, we've got 6 minutes left, but what do you think we'll see on these first two things? If this was the order of entry, what do you think we'll see on these first few things? I'm going to save this and just compile it real quick so I can kind of combine the time. Just so in case I do have any errors, I can quickly resolve them before we run out of time today. Uh, 2020, that should be right. Yeah, 2020 vision, right? Bobby kind of forgot about me. I was so idle for a long time. So we're going to G++ this real quick. std is equal to C++. 11 stack and q.cpp. Oh, it did compile. Hopefully we won't get any seg faults. Right, so here we'll see the 20, and we'll see the actual 20 come off. And then what we'll see? We'll see that 2, and then we'll see that 5, right? And then the last one, we might see a 3, except I pushed the 999 here, right? So I'm going to see the 999. And then I'll see that 3. So let's give it a shot. Please work. Will you seg fault? I hope not. Oh my gosh, it didn't seg fault. Hooray! Right, so that's exactly what I said we'd get. It did it. 20, 22, 5, 999, 3. So there, we've got a working stack. So now let's do the pop. Let's do the I'll just copy this. And here I'm going to use some knowledge. Maybe I'll throw some knowledge at you guys instead. Oh, and I have a memory leak going on here, guys. I'm sorry. Maybe I don't, because if I end up popping all of the elements, then it will be taken care of. But let me just do this at the end for fun. Delete our stack. Delete our queue. All right, so what we're going to do here, stop that, please. I'll show you some knowledge. Control F, find stack. Replace queue. I'll just go one by one because I don't want to do the entire thing. Oh boy. All right, where are we? Okay, and we'll just replace one by one. Q, 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 Q. Okay. Let's give it a shot. So what will we see here? Why don't you tell me? The peak, it's not going to work. Okay, so let's get rid of the peak because I didn't have time to do it. But what will we see on the first pop? If all goes well, and nothing seg faults. And this is FIFO. I'm sorry if that confused anybody. We'll give you a few more seconds. Cbase says 3, that's right. So we should see the 3, and then we'll see the 5, and then we'll see the 2, and then we'll see the, what will we see here? Here's the real question. What will we see on this one? 352, yeah, Red Rose was, got it. This is the big one. Yes, yeah, you're right. You're right. For a second there, I was like, no, but yeah, you're right. We're in the 999 is going to go in behind that 20, right? So in fact, this is where it changes. This is where it changes. So let's give it a shot. And let's call it a day. Please don't seg fault. It did seg fault, but it looks like most of it got working. So I'll spend just a moment to figure out where the seg fault happened. And you can hang out with me while we do that. You will have to use linked list in your next assignment, so if you do want to hang out, it might be good. But we did get that same ordering, right? 352 2090 999. So that's stack and queue. Does anyone have questions about stack and queue? Please let me know. I'm gonna just Valgrind this real quick, just to let it tell me that I didn't dash G it. So Red Rose asks, is there a reason why we use C++11 instead of newer versions? Oh. Yeah, so the newest C++ version did come out recently. So I would say to you, no, not really. UNLV needs to move forward. We need to grab the newest C++ versions and teach that. I would say you're correct about that. So it looks like we're getting some invalid reads from the clear list, which was called by the destructor. And so for some reason our clear list inline instead of queue. Well, let's see. I do have this peak here. Let's just look at my destructor. It says while head does not equal null pointer, then we're getting some invalid reads here. This is where the invalid read is coming from, I believe. It's telling me that on line 21 I get an invalid read. And so for some reason it's actually going into this head. So it looks like the head is not getting set back to null. So in our push, it should be okay as long as everything is allocated. We do initialize the head here, so it should be fine. And if we push something into it, then we're just going to make it the new head. Right? So that should be fine. So it's probably got to be on the pop. It's definitely in here because it only seg faults on the queue. It only seg faults on the queue. So this will be fine, and then we'll save this. I probably don't. Oh, I know what happened. What if this happens to be the head node? That's what happens. So we'll say, hey, if the head does equal the traversal node, then we want to assign that head to be null pointer. Let's see if that fixes our problem. Because it does not get set back to null pointer, and then the clear list thinks that it's actually something. There we go. All right, we fixed it. Also on that Red Rose, all of the servers will need to be updated. I think they have been updated. And so in the next few semesters, we will be, at least I'll have to check with the CS202 coordinator, but we will be moving forward teaching newer versions of C++. Maybe on Wednesday I can give you what's new in C++ 21, at least a general overview of what they've done in there. I think there's a few things that we could talk about. But then other than that, that's it. Thank you for bearing with me today. If you've got Stack Q questions, please let me know. Assignment will be going up soon. Please come to class on Wednesday. We'll just kind of do a few short things, nothing new. That's all I got for you. Office hours are in 12 minutes. Yeah. And on Wednesday, let's maybe talk about the newest version of C++. Thank you, everybody. I'll see you guys next time.